Let's talk about addition. Addition is the most fundamental operation in mathematics. You add things in your head every day without even realizing it. You can even say subtraction is just fancy addition with negative numbers. All other arithmetic operations are based on addition, like multiplication. When you multiply, what you're doing is adding something by the same amount many times. For example, 3 times 5 means add 3 to itself 5 times. So 3 times 5 equals 15. If you reverse it, 5 times 3, this means add 5 to itself 3 times. This gives you the same answer. Just like subtraction is really addition, we can think of division as just fancy multiplication. Dividing by a number is the same as multiplying by its reciprocal. If you multiply something by the same amount many times, it's called exponentiation. This is raising something to a power. In this case, we have 5 2's being multiplied together. So that's 2 to the 5th power, which equals 32. This is not the same as 5 to the 2nd power, or 5 squared. That means 5 times 5, which equals 25. So we have 3 basic operations in arithmetic. We have addition, and when we do this many times, we get multiplication, and when we do that many times, we get exponentiation. Now let's talk about numbers, starting with the most powerful number, 0. 0 plays a central role in mathematics, and it has special properties that make it unique among the other numbers. It's the smallest non-negative number, and it's also the only number you cannot divide by. 0 is sometimes referred to as the additive identity, because when you add it to a number, that number retains its identity. It doesn't change. These properties make 0 a powerful tool in solving equations. For example, if you set an equation equal to 0, and then factor that equation so that it's written as a product, then you know that either one of those factors must be 0, because if you multiply something by 0, you can only get 0. This simplifies the equation and allows you to focus on one factor at a time. 0's importance in mathematics cannot be overstated. The second most powerful number is 1, the smallest positive whole number, the unit. 1 is known as the multiplicative identity because when you multiply it by a number, that number retains its identity. Anytime you simplify a fraction, you're exploiting this property of 1. 1 is a whole number like 0, but there are other important numbers that aren't, probably the most famous of which is pi, less commonly known as Archimedes' constant. Here's how pi is defined. Take the circumference of any circle and divide that by the diameter of the same circle. No matter how big or small the circle, you will always get pi. An interesting fact is that whatever units you're using to measure a circle, the circumference and diameter can never both be whole numbers. The reason is because pi is an irrational number, meaning it cannot be written as a fraction. As a result of this irrationality, the decimal representation of pi goes on and on forever without stopping or ending in a repeating sequence. It turns out this isn't really a problem because you only need to know pi to the 39th decimal place in order to calculate the circumference of the entire visible universe and still be accurate to within the diameter of a hydrogen atom. The applications of pi in math and science are countless. There's another constant that's much less famous than pi, but no less important, known as e, more formally known as Euler's number. Just like pi, e is irrational. It cannot be expressed as a fraction, and its decimal goes on and on forever. The value of e comes from its official definition, which is the limit as n approaches infinity of 1 plus 1 over n to the power of n. I'll explain what this means. This limit arises from the study of compound interest. Let's say you have $1, and you decide to put that dollar into a savings account where after 1 year, it'll earn 100% simple interest. So your $1 will earn itself a whole nother dollar. Your account balance will be $2. Now imagine that instead of being paid 100% interest at the end of the year, you decide to split that up and be paid 50% interest after the first 6 months and 50% on the new balance after another 6 months. This is called compounding the interest. So in this case, after 6 months, your dollar will earn 50% of itself, bringing your balance up to $1.50. Then after another 6 months, your $1.50 will earn 50% of itself, 75 cents. This brings your balance up to $2.25. What if we split the interest up further and compound it monthly, 12 times a year? Then your balance will be $2.61. What about daily, 365 times a year? That'll give you $2.71. You can see the more your balance is compounded during the year, the more money you'll have at the end of the year. So then what if we compound it continuously? Not every minute, not every second, continuously. That's an infinite number of times per year. So what then? Would your savings account overflow with an infinite amount of money? Unfortunately, no. There's a limit to how much you can earn on 100% interest, and that limit is $2.72. If this number looks familiar, it's because this is e rounded to the nearest cent. This number has countless applications throughout mathematics. In calculus, we say the function e to the x is its own derivative. All that means is, anywhere on this function, its slope, or its derivative, is equal to the value of the function at that same point. This makes it the easiest function to differentiate. The derivative of e to the x is e to the x. This seemingly trivial property can be a powerful tool in solving complicated integrals in calculus. The many applications of e extend into the sciences as well. In biology and chemistry, e pops up anytime you're dealing with any kind of exponential change, such as population growth or radioactive decay. For these reasons, e is sometimes referred to as the natural constant, and it's also the base of the natural logarithm, ln. So far, the 4 numbers we've talked about, 0, 1, pi, and e, are all real numbers on the number line. The number line is one-dimensional and it extends forever in both directions. There's also a number line in the other dimension, perpendicular to this one at 0, which also extends forever in both directions. It's called the imaginary axis, and it contains all of the imaginary numbers. Despite their name, imaginary numbers are just as real or abstract as any other number. And just like the unit of the real number line is 1, the unit of the imaginary number line is I, the imaginary unit. Algebraically, I is defined as the square root of -1. This may come as a shock if you've always been told that you can never take the square root of a negative, kind of like how you can never divide by 0. While it's true you can't divide by 0, you can take the square root of a negative, and I is what makes this possible. If you combine a real and imaginary number, you get a complex number. All real, imaginary, and complex numbers exist on the two-dimensional complex plane. These 5 numbers are all unique and important in their own special way. They've all earned their place in mathematics independently of one another. You could argue that these are the 5 most important numbers in the universe. So what if I told you there's a mathematical equation that contains only these 5 numbers, each one once and only once? And in that equation, these numbers are related to one another using only these 3 basic operations, each one once and only once. It goes like this. First, we multiply the I and the pi. In algebra, when we multiply 2 variables or constants like this, we usually don't write the multiplication symbol. Now raise e to the power of that product. Then add the 1. And finally, all that equals 0. This is a true mathematical statement known as Euler's identity, or sometimes called Euler's equation. Look at the elegance and beauty and simplicity of this equation. How can these 5 numbers, with such significant roles in math and science that have nothing to do with one another, be related in such a simple, straightforward way? 19th century Harvard mathematician Benjamin Peirce famously said during one of his lectures, "Gentlemen, that is surely true. It is absolutely paradoxical. We cannot understand it, and we don't know what it means, but we have proved it, and therefore we know it must be true." A more recent quote from Stanford University professor Keith Devlin goes like this: "Like a Shakespearean sonnet that captures the very essence of love, or a painting that brings out the beauty of the human form that is far more than just skin deep, Euler's equation reaches down into the very depths of existence." Is this equation too simple, too elegant to be just a mere coincidence? Must there be some kind of intent behind such an impressive natural occurrence? Is this evidence of something greater? I think that's something we should decide for ourselves. Thank you for watching. If you enjoyed this video and you'd like to support my growing channel, hit like and subscribe. And please leave a comment and let me know what you think about Euler's identity.